Okay, in this lecture, we're going to cover section 4.9. This is the last section in chapter 4, and then we'll move on to the final topic in this course, which is on integration. So 4.9 is on antiderivatives, and this is actually more or less going to be about integration itself. So we're going to be looking at as we're going to be given a function, and we want to be able to find a function whose derivative equals the given function, and this is that such a function is called an antiderivative. And this process is really just more or less finding the indefinite integral of a function. So this is really, like I said, it's basically integration, and integration is basically differentiation in reverse. And this is sort of what makes integration challenging, is because a lot of times you have to just guess. Eventually, you'll be able to see some patterns when integrating functions and be able to like come up with some general rules. But integration can be a lot more difficult because it's guessing and doing differentiation in reverse. So integration is a bit trickier than differentiation. So the idea behind, but for in terms of applications, so there's a lot of reasons why you want to find antiderivatives of functions. So for example, if you're a physicist and maybe you know the velocity of a particle, you want to, and given the velocity, you want to know, be able to track its position. Well, position is going to be an antiderivative of velocity. So the derivative position is velocity, and then going in reverse, the antiderivative of velocity is position. So if you know the velocity of this particle at any given point in time, like say you can explicitly describe this function, you can take the antiderivative, or not the antiderivative, but an antiderivative. It's going to turn out that these antiderivatives are not unique. So you could find an antiderivative of the velocity, and that will give you the position of the particle. So lots of applications. I try not to talk about. I try not to go down too many rabbit holes in terms of applications, but like there's just the types of applications are endless. They're you know. So let me share my screen now, so we can start learning about this. Hopefully, you can see what I can see. So here's the definition. So if you have a function, you see, so you start with a function f, lowercase f. A function capital F is called it's an antiderivative, not the antiderivative. If it satisfies the following definition, that is, more or less, it's a function whose derivative is equal to the original function. So function capital F is called an antiderivative of lowercase f. It'll be on some interval I, so probably just the domain of f, if when you differentiate that function, you get f, and that's for every x in the interval. So in other words, this says, let's maybe phrase it just slightly differently. An antiderivative, so an antiderivative of a function. It's always good to read definitions symbol free. So we're going to try to read this symbol free. So an antiderivative of a function is a function. It's another function, possibly the same function, who knows? But it's just a function whose derivative is equal to the given function. Is equal to the given function. So this is like requires some to find antiderivatives. You got to be a little clever, think about outside the box, and play around with some examples. Practice differentiating. So it's definitely going to be you definitely need to know your differentiation rules pretty intimately. You got to be pretty familiar with them in order to determine an antiderivative. So it's a function whose derivative is equal to the given function. So here's an example that they point out, like a really easy example. So suppose I give you this, f of x is equal to x squared. So so let's just try to figure this out right here without reading the book. So we need to find f of x such that when you differentiate it, you get lowercase f of x, which is equal to x squared. All right. Well, when you look at this, you should think that you should probably think of x to some n, right? Or some combination of it, because according to the power rule, when you take a derivative of something x to the n, you're gonna reduce the power, so you get x to another power. And that's what we have here. We have x to some power. So I want the function to be sort of the same form in this case. So if you were to just guess and play around, and you notice there's no coefficient here. So well, there is a coefficient, it's just one though. So when you take the when you do the power rule, you take say derivative of x to the n, it's going to be let me just write it over here. So the derivative of x to the n is equal to n times x minus 1. So this should suggest that I need x to the third, right? Because if I do the power rule to this, I bring the 3 down, so I have x to the second, and that's close. I have that. But then there's that pesky coefficient of 3. So what I need to do is I need to have a factor of 1/3 here to cancel out with the coefficient that you get from using the power rule. So here's a guess, and let's just check it. So if I do f prime, I'm going to do the power rule. So I have 1/3 times 3 times 3 minus 1, which is 2. And then the 3 and the 1/3 cancel, and you get x squared, and which is f of x. So check. All right, so this is an antiderivative. Why is it just an antiderivative? Well, I could have chosen something else. I could have, say, chosen capital G of x, and I could have chosen 1/3, whoops, 1/3 x to the third plus, I don't know, anything you want, pi. So if I take the derivative, um, according to the power rule, I bring the power down. So it's 1/3 times 3 times x squared. And now I have this constant here, but it's a constant. When you differentiate a constant, it is 0. And that is going to be x squared, and that's also going to be f of x. So it's kind of bad. So no. So g of x definitely does not equal f of x. So that's kind of unfortunate. But g of x minus f of x is a constant. It's pi. So you might wonder, without knowing this, you might say, okay, we have this antiderivative here, and then this antiderivative here. Dang it, they're not the same. You can have lots of different antiderivatives. You can just take pi and replace it with any constant you want. But as we noted here, that although these antiderivatives are different, and there are going to be infinities of antiderivatives, they all differ by this constant. So when you take the difference of them, it's just some constant. And so you might wonder, is that the only type of antiderivative? In other words, if I know an antiderivative, if I have an antiderivative, is every other antiderivative going to be so sorry, let me back up. So if I know an antiderivative, say I have an antiderivative f of x, capital F of x, and this is an antiderivative of lowercase f of x, you might wonder then, all right, is every other antiderivative of the form capital F of x plus a constant? If that's your guess, you would be right. This is the right thing to do. So why is that? Well, here's how you can actually prove this actually that every so here's like a claim we can actually prove this whoops so the claim is as follows: if you have an antiderivative, so suppose you have a function f and you're able to guess an antiderivative f, through some just playing around experimenting with the function and trying to guess what antiderivative is, and you finally stumble upon one. If you have one such a antiderivative, then the most general antiderivative. There's not a single unique antiderivative, but the most general form of the antiderivative is going to be the one function that you guessed as an antiderivative plus a constant, or this, yes, C is any arbitrary constant. So this is a nice result because although there's infinities of antiderivatives, they are more or less the same. And in fact, you can in mathematics, it's really convenient to define a general notion of equals. So you can define this gives what you what's called an equivalence relation. So equals is a type of equivalence relation. It's a relationship between things, and you state that they are identical. This is the relationship of being identical. But you can have more general notions of equivalence. So you can say that if you have a function, then you can look at all the antiderivatives, and you can say that they're all the same really because they differ by a constant. So they're equal. You can say is they are equal up to a constant. And really, what you're doing is you're looking at the space of antiderivatives of this function, and then you can like there's this thing where you quotient or mod out by this equivalence relation. Like you just all the functions collapse to one function because they all are differ by a constant. So you define two, in other words, you define two functions, antiderivatives of f to be equal if they differ by a constant. And this theorem says that though that's the only type of antiderivative you can have. They all have to differ by a constant. So really there in that sense um there is one antiderivative if you don't care about the constant. And you really usually don't. Sometimes you do. It depends on the application. But there is a sense in which you could say that there is one antiderivative because they're all equal up to some constant. They all differ by some constant. And so this does give you some notion of equivalence. All right, so how do you prove this? Well, it uses the mean value theorem. So this is a really clever, cool application. It's a simple, very simple application of the mean value theorem. So this is that theorem which said that if you have a function, you know what, let me just pull it up actually. I'll just Google it, mean value theorem, so we can have an exact statement. I don't want to have to write it down and waste time. So here's Wikipedia. Don't hate Wikipedia. It has actually some really nice mathematics articles. So if you're trying to learn stuff, I would definitely, just in terms of learning for your own sake, Wikipedia is a perfectly fine source. Don't use it as a formal source though. But I use Wikipedia all the time. So what is this? What does mean value theorem state? It says that you have a function and it's continuous on a closed interval, and it's also differentiable on the open interval where a is less than b. Then there exists some number c in AB such that f prime of c is equal to this average rate of change. So the thing on the right hand side, f of a minus f of b over b minus a, is the average rate of change over the interval. And it's what it says is that your instantaneous rate of change at some point your instantaneous rate of change equals your average rate of change. And the best example to think is to imagine like this function is describing velocity as a function of time. So you know you can calculate your if you travel from one point to another point, and you can, you know, you have a change in position, your displacement, you can calculate that displacement. You can calculate how long it took you to travel through that displacement, and then you can get an average velocity. And what the mean value theorem says is that at some point in your journey, your instantaneous velocity had to equal your average rate of the average velocity. That's all it says. And then there's, of course, this geometric way of thinking about it that you have this slope, you have the secant line through f of a and f of b, and then that has a slope, the secant line has a slope, and what this says is that at some point between a and b, there's a tangent line which is parallel to that secant line. So that's what just to remind you of what the mean value theorem says. So how does it help us prove, whoops, how does it help us prove this theorem? Well, this is how you start. You say, okay, let's suppose we have two antiderivatives, f and g of capital F and capital G of f. So if they're antiderivatives, right, if we're assuming that these are just any two antiderivatives, then by definition, this equation holds. That's what it means to be an antiderivative. If you differentiate those two functions, you get the original function you started with. But what is this? This says that in particular that f prime of x, capital F prime of x, is equal to g prime of x, capital G prime of x. But remember, there was that it was a corollary. See, corollary of the mean value theorem. It said that if you have two functions and they have the same derivative, then their difference has to be a constant, right? So for some constant c. Who knows what it is, but there's some constant. And then of course you can rewrite this so that you could say g of x is equal to f of x plus c, and that proves the result. So very simple application. If you don't understand it, that's okay. But if you just ponder that for a little bit, pause the video. It's a fairly simple proof that uses a nice application of the mean value theorem to allow you to describe all the antiderivatives of a function. So what this says is it says is that is as soon as you know one antiderivative, you know every antiderivative. All right, so let's use that. Yeah, so here's this. So going back, we have this function right here. We know that this is an antiderivative, right? We actually prove that on the side of this, on the side over here, right there. We prove that. So that means, oh, sorry, we proved it right here. So we know then that the most general antiderivative of f is just that antiderivative plus any constant. All right, so let's look at these examples. Let's work through these examples right here. Let me open up Paint. Put this to the side. All right, so now, so this is 4.9 on antiderivatives. And this is example 1. All right, so we have a couple parts. So we have A, we want to, let me actually write the statement down. Find the most general antiderivative derivative of. Okay, so now for A, we have f of x is equal to sine x. All right. So for this, we need to remember our derivative. So we know, again, it just really comes down to remembering your derivatives and what they're equal to. So for this one, you need to remember that when you take the derivative of cosine, you get negative, you get negative sine. Right. So that's close. We just have this pesky negative in there. But we can just throw the negative in there and we'd be fine. So we're gonna let capital F of x equal negative cosine x. And when you take this derivative, it's gonna be negative, it's gonna be the derivative of negative cosine of x. The negative comes out. Oops. Now you're just taking the derivative of cosine of x. And we know as I just pointed out right here, we know the derivative of cosine of x is gonna be negative sine x. And so the negatives cancel and you get sine x, and that's equal to f of x. So this is an antiderivative, so this implies that negative cosine of x plus c is the most general one for, let's say, for any constant c. Okay, what about b? So for this one, we need to remember, so for b, we have f of x is equal to 1 over x. So for this one, we need to recall, so we need to find a function whose derivative equals that. So if you don't remember your derivatives, you can consult a table, and if you look through that table, you'll remember, or you'll see at least, that the derivative of ln of x is equal to 1 over x, and that's of course on whoops, the interval. Yeah, it should be specifying on interval. This right here, this one I called on here, is on the whole interval, the whole real line, so that's good. This differentiation formula is only valid for the when x is in this interval right here. So this implies that so we have ln of x is equal to, when you differentiate this function, you get this. So this implies ln of x is an antiderivative. It's one of the antiderivatives. It's a function whose derivative equals the given function. So this implies that ln of x plus c for some constant c in here is the most general one. Okay. So this right here is the most general antiderivative. All right, so what about the last one? So this is part C. We have f of x is equal to x to the n. All right, so actually this is not completely done. I'm sorry. There is a more general, actually we can get a better result than this. All right, there's a better result. So this only works for, this only works for 0 to infinity. So here's a better result actually. This one maybe, this antiderivative is maybe not as familiar, but it says that if you take the derivative of ln of absolute value of x, it's going to be 1 over x, and this is on negative infinity to 0 union 0 infinity. So this is a differentiation rule that holds on a larger interval, basically the whole real line except 0. So this is a better result. So this implies that ln of absolute value of x plus c for c in here, any constant, is the most general antiderivative of f of x given by 1 over x. And that's good because this is that you can't enlarge in this domain anymore because f of x itself is not defined on a larger domain. So this is actually a much better improvement. It's an improvement of what I just showed you. All right, so now we want to go to part C. So for this one, we have f of x. We want to find the most general antiderivative of this. So for this, we need to recall, let's see, is there any, actually, okay, and this is for n not equal to -1. And in fact, this is okay to stipulate because we already dealt with the n equals -1 case, right? That was part B. So now we want to know what is the general antiderivative of this when n is not equal to -1. So we already dealt with that. For this one, we need to recall the power rule. So it says that when you differentiate x to the n, you get 1 over, and in fact, actually, let's use m. X to the m. It's going to be m times x to the m minus 1. All right, so what this should suggest is that we want to differentiate. We sort of did this problem with the x cubed, right? So if we differentiate x to the m plus 1, that's good, right? It's going to be close because we got to bring this power down and then reduce the power. So, sorry, not m. I don't want to use m anymore. I want to use n plus 1 now. So this suggests, this formula right here suggests that we should use x to the n plus 1 because when we differentiate, we're gonna reduce the power by 1. So that means when we differentiate this, so I'm going to leaving this intentionally blank because I want to put something there. If we use the power rule, uh, we bring down the power, so it's an n plus one, and then it's going to be x to the n plus one minus one. So x to the n. All right, that's close. So we move on. We just have this pesky coefficient. This is the same pesky coefficient that showed up in the very first example. So all I need to do to remedy this, though, is just throw the right constant in this blank to cancel it out. And what that's going to be is uh, 1 over x plus 1. Sorry, 1 over n plus 1. So then when you differentiate this now, you have this constant. You can pull this out and it will go here. And so this 1 over n plus 1 will cancel with this n plus 1 right here. And what you get is x to the n. So this implies that 1 over n plus 1 x to the n plus 1 is an antiderivative of f of x is equal to x to the n. And then this will imply that 1 over n plus 1 x to the n plus 1 plus c, for c, any real number that's a constant, is the most general. This is the most general antiderivative. All right. So let me pull up this formula, this table of formulas. These are going to be anti-differentiation formulas. All right, so here we go. So some of these we saw already. So we did this one right here. And we saw that this is the most general antiderivative. We saw this one function and this right here, or sorry, it's a particular antiderivative. But it's easy. It is easy to describe all the antiderivatives, and we have this nice sum rule, right? If you have a sum of two differentiable functions, their antiderivative is just the sum of their antiderivatives, and that makes sense because the reason why that's true is because um, the sum of derivative functions is the derivative of a sum of functions is the sum of the derivatives. This rule should make sense as well because if you have a scalar multiple function, when you take the derivative of a scalar multiple function, you can pull the scalar out and then just differentiate the function. So if you differentiate this, you will get this right here, assuming capital F of x is an antiderivative. Then we have e to the x. That's a really easy one. It's its own derivative, so it is its own, sorry, antiderivative. And then we have cosine x. When you differentiate sine x, you get cosine x. You don't have to worry about negatives in this case. All right, let's see. What are some other examples? All right, so what we want to do is for this next one, this is example 2. So if we want to find all functions g such that g prime of x is equal to sine 4 times sine x plus 2x to the fifth minus square root of x divided by x. So we want to find that. So in other words, we want to find an antiderivative. Whoops, I don't know if I'm spelling this right. Of 4 sine x, or we want not to find an antiderivative, but all the antiderivatives, sorry. 4 sine x, but of course, once we know a single antiderivative, we do know every antiderivative. So this is sort of accurate to say, actually. So we want to find the antiderivative, or an antiderivative of 4 sine x plus 2x to the fifth minus square root of x over x. And I'm gonna write this, I'm gonna break this down. So, because when it turns out when you want to anti-differentiate, the process of anti-differentiation is also linear. That is, if you want to, and we saw that already actually in the table I showed you, that if you want to anti-differentiate a sum of functions, you just anti-differentiate each, you just anti-differentiate each piece. All right, so now this can be written as 4 sine x plus 2x to the fourth, and then minus x to the negative 1/2. Put this down some more. All right, so now I just need to anti-differentiate each piece. And it's gonna really just be a guess. So here's my guess, and you gotta check. You gotta guess and then check. So I'm gonna throw something down, and it's gonna maybe seem slightly mysterious, but it shouldn't. So my guess is this. Um, plus now, so we know, well, it's not too mysterious, I guess. If you know, so we know that this is G prime, so the guess is that this is going to be G itself, just G alone. And so we need to take the derivative, we need a function so that, or one of the pieces in G of X has to be cosine of X, because with a negative, because when you differentiate that, you get negative sine X, and then it will cancel this negative, and you'll get this back right here. So this part works. All right, now I need to worry about this. Well, just pull the constant out. I don't care about the constant, and just anti-differentiate x to the fourth. Well, according to the rule, it's going to be 1 over the power plus 1 times x to the power plus 1. And the same thing for this piece right here. It's going to be 1 over 1, oh, sorry, 1 over the power plus 1 times the power plus 1, x to the power plus 1. And then uh, always just add your constant in, and then you'll have the most general antiderivative. So now this implies that g of x is, after we simplify a bit, it's going to be plus 2/5 the x to the fifth. And then this is going to be negative 1 over 1/2, so it's going to be 2 times x to the positive 1/2. And then I guess you can write, oh, plus your constant. Never forget your constant. And then I guess you could write it like this. Minus 2 times the square root of x. Let's see here. And if you're unsure whether or not this really is the antiderivative for here, or it describes the most general antiderivative, just differentiate it, and you'll see that you'll get this back right here. So just pause the video and check that if you have to. All right, let's see. What is another? Let's see another example. All right. I guess we'll just do one more example. I'm going to skip 3, but I encourage you to look through that. So I'm going to go to 4. So this one's will be, I want to go over this one because this is a little more complicated. So I had to anti-differentiate twice. And in this case, I'm actually given what are called initial conditions. So initial conditions are parameters that allow you to determine those constants. So when you anti-differentiate, every time you do this anti-differentiation process, you pick up constants, one for every time you do anti-differentiation. But if you know parameters, which are called the initial conditions, you can determine those constants. So for example, you could have an initial condition could be something like you're at you occupy this position in space at this time. So it can be like, you know, something, maybe you don't know the position function itself, but when you were performing an experiment, you observed that the particle was at this point in time. All right, so then you can use that to determine the constant, or you know the temperature of the room at this time. Okay, that's an initial condition. So yeah, they're called initial conditions because they're usually they're conditions about say a physical system that are known at the beginning, at its beginning. So you have like say motion of a particle that begins in time, right? It has a time at which it begins, and usually you know something about its like initial position, say, and so that initial position will be translate to an initial condition. Or if you're measuring the temperature of a room for whatever reason, I mean these are kind of just ad hoc examples, but you maybe measure um the initial temperatures, and that would just give you an initial condition. All right, so we're not going to really phrase it in that way, but I just want to let you know that this comes up, and this will actually be really important if you go to take differential equations. You're going to solve. So differential equations are equations where instead of solving for a number that satisfies the equation, you're going to solve for a function that satisfies an equation. So this will be like a functional equation in a sense, and it will be you want to find a function which satisfies the equation, and you might pick up constants because differential equations and a lot of times involve this process of anti-differentiation. So you'll pick up constants, and you want to determine those constants. So I mean, and differential equations are extremely important in engineering and science. They come up everywhere. So differential equations are very important. Um, and they describe a lot of phenomena. So like you can there's the so-called wave equation, and this is it's a differential equation describing waves and standing waves. So this could be like mechanical waves, like water waves, sound waves, seismic waves, or electromagnetic waves. This wave equation will describe a wide range of phenomenon, a wide range of different types of waves. Anyways, that's all out of the scope of this course, but I just want to let you know that there's these things that come up. So what we want to do in our case is find a function if uh, if we're given that its second derivative is 12x squared plus 6x minus 4, and our initial conditions are f of 0 is equal to 4 and f of 1 is equal to 1. So like this could be your position on the real axis at time 0, and then this could be your initial position, or sorry, not your initial position, but your position. You're at 1, so you traveled backwards after a second went by. For example, it could be anything really. So what we need to do is we need to find, before we can find f, so before we can find f, we need to find f prime. So that's how we're going to do this. So we're going to anti-differentiate each piece. So we have f prime of x is going to be, so I have the 12, so just I can ignore the constant because when you anti-differentiate, you can pull the constant out of this process. And so it's going to be x to the third, x to the 2 plus 1, and then it's going to be over 3, 2 plus 1, the power plus 1. I'm not going to write it in the front as a coefficient. I'm going to write it in a fraction like this. So I can save some space, and I can, for for the constant 12. I'm going to do the same thing for the 6x. So then this is going to be 6x, and then it's going to be x to the 1 plus 1. You add 1 to the power, and then you divide by 1 plus 1. So you can see this is really the reverse process of differentiation. So when you differentiate x to then, you multiply by n, and then you reduce the power. When you anti-differentiate, you add 1 to the power and then divide by the power. So it really is reversing everything. And then we have 4. Now in this case, we don't really just have 4, we have 4 to the x times x to the 0. So now it's going to be 4 times x to the 0 plus 1 divided by 0 plus 1. So if you have to, just to keep track of like bookkeeping purposes, you can throw that in there. When you have a constant, you can just do 4 times x to the 0. And of course, don't forget your constant. So this is going to be end up being called the constant of integration. All right, so now we have 12 divided by 3, so that's going to be 4x to the third, plus 6 divided by 2, so it's going to be 3x to the second power. And then we're going to have 4 minus, just minus 4x plus c. All right, so we have f prime of x. All right, so that brings us one step closer to getting f of x. So now f of x, we're going to anti-differentiate one more time. So I just do the same sort of process. So I ignore the coefficients. So it's going to be 4 times x to the 3 plus 1 over 3 plus 1 plus 3 times x to this 2 plus 1 over 2 plus 1 minus 4 times x to the 1 plus 1 over 1 plus 1. And now, again, I have this constant c, so I can just throw an x to the 0 if I want. So this will be c times x to the 0 plus 1 over 0 plus 1. And now I need to add another constant because I just anti-differentiated again. So now I have two constants I need to determine. And so let's simplify this first, and then I will use my initial conditions to determine these constants. So this is going to be x, so 4 divided by 4 is just 1, so I get x to the fourth plus, the 3 cancels with a 2 plus 1, so I get x to the third, and then I get, this will be minus 2x squared plus c times x plus d. And so now let me just write those initial conditions down again, so I don't have to keep scrolling up. So we have the initial conditions are f of, sorry, where am I? No, f of 0 is equal to 4, and f of 1 is equal to 1. So we get 1 is equal to, or sorry, let's do the first one. So we have 4 is equal to f of 0. Well, just plug 0 into here, so you get 0 to the fourth plus 0 to the third minus 0 times 2, minus 2 times 0 to the second power plus c times 0 plus d. Well, all these terms right here are going to die, so it's just d is equal to 4. Okay, that's good. So we determined one constant. Now we also know that 1 is equal to f of 1. And so I've just plugged the 1 in, so I get 1 to the fourth plus 1 cubed minus 2 times 1 squared plus c times 1 plus d, but we know that is equal to 4. All right, so now we have 1 is equal to, so we get a 1 plus another 1, so that's 2. And then I got minus 2, so that's 0. So then I have 1 is equal to c plus 4. And then that will imply that c is equal to negative 3 if I did that right. Let's see. Yes. So that implies that now we're talking about a specific antiderivative because we've determined these constants of integration. Sometimes if you're dealing like studying physics, they'll be called constants of motion sometimes. Like either you're trying to describe the motion of a particle and you can describe its function. You can describe the function, but you have these constants. And then if you know its initial position or initial velocity, maybe, or something like that, you can determine those constants of integration. All right, so what we have is f of x is equal to x to the fourth plus x to the third minus 2x squared plus, sorry, no, that's minus 3x because c is negative 3 plus 4. All right, so that's all we have for this lecture. So somewhat short, although I did go on some tangents, and always feel free to just, I know I'm like saying this after the fact, but always feel free to skip over my tangents if you're not interested. I go off on tangents because I know that there are some people who are interested in the deeper connections of mathematics, and like they like to look ahead to see what's going on later on in mathematics. That's all we have for today, though.